Um, Overall, the test went pretty well. If anybody has any questions about how I graded it or anything like that, come talk to me. Yes? Oh, you didn't get yours. Okay, I need to get yours. Here is the basic. Let me just do the free body diagrams. So exam 3. It looks like that. There's a triangular distributed load on the top member. There's a mass hanging there. The distributed load is 6,000 newtons per meter at the highest point. And this angle is 45 degrees. If you isolate the hanging mass, you have a downward force of 981, a cable tension of T. And you can see from that when you use Newton's second law, T is equal to 981. In statics, you can just always make that jump. A lot of people didn't do this free body diagram, and I didn't take off any points. In statics, you can do that. In dynamics, you can't. If you got rid of this arm, say, got rid of this diagonal arm, and put a motor on this so everything was accelerating, the tension in that cable isn't 100 anymore. So careful next semester. But for now, that the tension in that cable is always just going to be the weight of the thing hanging from it. So now that we have that cable tension, we have to choose a numbering for these members. I guess I'll do it 1, 2. So a free body diagram of member 1. We have reaction force here. I'll call that RA. That's a pin joint, so there's no couple there. We have the distributed load. I'll just leave it like that for now. And then at the other joint, there are two things. So if you think of a side view of this joint, let's call this joint A, this B, and this C. And if you think of a side view of B, you'd have member 1 and member 2 with a pin going through them. And then you'd also have that downward force acting on the pin of 981. We just figured out that that tension force is 981. We treat the pin like it's part of the lowest numbered member. So all of this is one thing. That all of the blue shaded region is member 1. And so this is a side view of joint B. And so acting on member 1 at joint B, there's a contact force with member 2, so that's F12, and then there's a downward force of 981. In order to do the math, you have to represent that distributed load as a point force. So that changes to RA, a point force of 6,000 times 1 divided by 2, so 3,000 newtons there. F12, 981. Oh yeah, you're right, weight force. And that was 30 per meter, so 294.3. And then member 2, the horizontal one. Yeah, right. And then free body diagram of member 2, the diagonal one. We have the reaction RC at the bottom. We have a weight force in the middle, so that's 1.4 times 30 times 9.81. I'm not sure what that is. What? 414.96. And then up here, the only thing that member 2 is touching at the joint B is member 1. You can see that on that side view. Member 2 isn't touching that 981, that cable. And so we just have negative force on 1 by 2. And that's it. And outside of that, everything is just geometry and setup. Any questions about that? Or any specific questions about this problem from the test? Okay, last time we started talking about internal loads. And the way we went through it was I gave this example beam where we had, was it downward forces of 5,000? Is that what it was? 500. Upward force of 1,000. Downward force of 500. And we wanted to calculate the internal loads at this point along that dotted line. Oh, I just want it to be 5,000 so bad. Okay, so we calculated the internal loads along the dotted line. Second, we acknowledge that being able to calculate the internal loads at a finite number of points isn't really what we want. We wanted to be able to calculate the internal loads at any point. And so we came up with an approach where we could calculate the internal loads at every point along the beam. And we came up with this for our results. So if this is the tension as a function of x, and that's 0.5 meters, and that's 1 meter, the tension was just 0 the whole time. The shear force was negative 500 for the first half, positive 500 for the second half. And the bending moment was a linear function like that, going down to a minimum value of 250, and then a linear function like that going back to 0. Notice that what these are is piecewise functions, and that's what we're always going to be coming up with here. So these are piecewise functions. And I'll represent them as t as a function of x, v as a function of x, and m as a function of x. And so you can rewrite these as, well, t was just equal to 0. But v was equal to negative 500 for x's in the open interval from 0 to 0.5, and then positive 500 in the open interval from 0.5 to 1. What happens at 0 and 0.5 and 1, we don't know. We don't care. And then m was equal to negative 500x for x values between 0 and 0.5, and 500x plus 500 for x values in the interval from 0.5 to 1. So if you have a piecewise function like this, the individual functions that make it up are called subfunctions. And there was a crucial thing that happened at those boundaries between where the different subfunctions represented what was going on. Remember, when we did this problem, our whole free body diagram, our whole representation of what was happening changed at these boundaries. Okay? And so these boundaries between subfunctions are a really important thing. So where do the subfunctions change? In general. So here are the candidates for subfunction boundaries. first are the end points of the beam. Second is the locations of any point loads. That can be forces or couples. And third, any place where the distributed load function changes. Between each pair of candidates, actually let me call them boundaries. Make a new cut. And what I mean by that is draw a new free body diagram and use Newton's laws. If there are n boundaries, then how many cuts are there going to be? N minus 1, yep, exactly. Okay, so let me go through another example, and we'll think about it in this way. We haven't done one yet where we've had to calculate the external loads on the beam before we started, but we're going to on this case, and this example. So let's say we have a cantilever beam, and there's a 500 Newton force acting up in the middle. This length is 0.2 meters, and this is 0.2 meters. And then at the end of the beam, let's say there's a couple this way of 500 Newton meters. And we want to know the internal loads. Well, before we can start doing the cuts and stuff, we have to calculate the external loads. So first we have to do the rigid body problem. So free body diagram of the whole beam. At the fixed joint, we have a force vector and a couple. I'll call that MR. In the middle, we have the 500 Newton force. On the end, we have another couple of 500 Newton meters. And no mass was given, so we're going to neglect the weight. This is a rigid body problem, so if you want, if you feel more comfortable, you can always, list out the row vector and the force vector and the moment vector. But since it's horizontal, doing that stuff in your head isn't too hard once you get used to it, so I'm just going to do it like that. So Newton's second law says R that 500 is in the positive y direction, so plus 0, 500. That couple doesn't produce a force, so that's equal to 0. And so this R vector is equal to 0, negative 500. And then the moment equation, I'm going to use this as the about point. What's the moment produced by R?
0.
Right? What's the moment produced by MR? That's not 0 because that can be tricky. It's MR. Those couples you just add on. So MR. What's the moment produced by the 500? Well, let's say, what's the moment arm? 0.2. The force is 500. Would that cause a clockwise or counterclockwise rotation? Counterclockwise, so it's a positive 0.2 times 500, which is 100. And then we just add on this 500. Is that clockwise or counterclockwise? Clockwise, so that's minus 500. And that's all equal to 0. So that tells us that MR is equal to positive 400. So going into the internal loads, we have this. Let me write this differently, actually. We have R is a downward force of 500. MR is this way at 400. And over here we have 500. And now we have to think about the boundary points, those candidates for changing subfunctions. Well, the endpoints are always included. And once you've counted a point, you don't care how many ways it's counted. We're just looking for points. So the fact that this also has 2 different point loads, that doesn't, the answer is still that that's just one of these key points that we're looking for. And where else is the subfunction going to change? Possibly. In the middle at that 500 Newton. So we're looking for the endpoints. We're looking for places where there are point loads. That's this. And we're looking for places where the distributed load function changes. We haven't dealt with distributed loads with this yet. Okay, so n equals 3. And that means we're going to have to do 2 cuts. And remember, with these cuts, we're going to do it, and if this is going to get confusing, I'm going to keep reminding you about this. Our first cut, okay, so cut 1 is going to represent x values between 0 and 0.2. Okay? But that doesn't mean I'm going to draw a free body diagram that goes from just to the right of 0 to just to the left of 0.2. What it means is I'm going to have a free body diagram that goes all the way from the left, including that left endpoint, to a right endpoint that falls somewhere, anywhere in between 0 and 0.2. Okay? It falls a distance x from the left endpoint, and that x can be between 0 and 0.2. So in every one of our cuts, we're going to go all the way from the left. And it's the right that x represents. Okay? So here's the first cut. We have the 500 Newton force. We have the couple of 400. We haven't gotten to the 500 yet. No matter what our x value is, this distance is x. And so the only other loads on our chosen piece are the tension, the shear force, and the bending moment. Any questions about that? So Newton's second law says there's a 500 Newton force down. There's T in the positive x direction. There's V in the negative y direction. And you can solve for those. You get T is equal to 0. V is equal to negative 500. And then we'll go to the moment equation. And our about point is where it always is for internal load calculations, all the way at the left. So that 400 Newton meter couple, does that produce a moment? Yeah, so just add that on. The 500 Newton force going down, does that produce a moment? No. T? No. M, yes, so just add on M. V has a moment arm of x, and would that produce a clockwise or counterclockwise rotation around the red dot? That's clockwise, so minus Vx. So M is equal to Vx minus 400. We already know what V is. So M is equal to negative 500x minus 400.
Why only M is we use x function of x, which is because just the moment we're calculating, we didn't use it for V or T.
Yeah, right, because it's the moment. With Newton's second law, we're just adding up these forces. But for the rotational equation, these moment arms matter, and that x is a moment arm. And, you know, you're going to end up almost certainly doing it this way. But if at first something doesn't make sense about how this works with the moment, just do a couple problems where you write out the table, do the calculation like a rigid body calculation. It takes a little more time, but that doesn't matter. What we're trying to do is just understand it, you know.
Yeah. And we always use x like as an arbitrary distance.
Yes, that's right, because this free body diagram has to represent all choices of bodies that go from the left endpoint to somewhere, and that somewhere falls anywhere in here.
Oh, okay.
You know, so that x represents 0.00001, and it represents 0.1999999, and everything in between. Okay, so what we have here are internal loads that are valid for all x's between 0 and 0.2. They're not valid at the endpoints of that interval, but we don't care. And now our second cut. This one represents all the x values from 0.2 to 0.4. And so I'm going to isolate a piece that, again, goes all the way from the left end. But this time, the right end is at 0.20001 or at 0.3999999 or anything in between. And so that's going to change the way the free body diagram looks. So since we're going all the way from the left endpoint, we still have, I can write it like that. We still have that downward force of 500. We still have that couple of 400. But now no matter where in this range x is, our free body diagram has to include this 500 Newton force. Okay? If our x represents 0.20001, then that 500 Newton force is really close to the end of what we're isolating. If our x represents 0.3999, then that 500 Newton force is really close to the middle. But either way, this appears, and you can just put it wherever. I'll put it here. And then we have T, V, and M. So Newton's second law says that 500 is in the negative y direction. This 500 is in the positive y direction. And then we have T in the positive x direction, V in the negative y direction, and that's all equal to zeros. So T is equal to 0, V is equal to 0. And now we'll go to the moment equation. The 400 Newton meter couple gets added on. It's counterclockwise, so it's positive. The 500 doesn't produce any moment. That 500 Newton force that's at the middle of the beam, no matter where the right endpoint is, that 500 Newton force is 0.2 meters from the left end, right? And so the moment arm of this 500 Newton force is 0.2. So it's going to be 0.2 times 500, and would that make a clockwise or counterclockwise rotation? Counterclockwise, so that's plus 500 times 0.2. And then we have plus m minus vx equals 0. So m is equal to vx minus 600, 500. And so m is just equal to minus 500.
If x is going between 0.2 and 0.4, while we went from 0, like from the left, like all the way from the left to...
Yeah. So we're calculating these internal loads just based on where the right end is. Okay. So it doesn't matter for our calculations where the left end is. Okay. All that matters is where the right end is. So the right end is in that range. That means the left end we're just choosing based on where it's easiest to do our calculations. And notice that if we didn't go all the way from the left end for our cut, say we went from here to here,
Yeah.
you could do that, but then you'd have internal loads to calculate over here and internal loads to calculate over here, and it just would be unnecessarily complicated.
Yeah.
So we're always going to go from all the way at the left to our arbitrary value x.
Oh, okay.
Okay.
But we always assume that x will go from 0.2 to 0.4.
Yes.
Because we're on the right side.
That's right. And so now what we have, based on these calculations, is that t is 0, v is 0, m is negative 500, and those values are valid for all x's between 0.2 and 0.4. And you could write those as piecewise functions. T is equal to 0. V is equal to negative 500 for x between 0 and 0.2, and 0 for x between 0.2 and 0.4. And m is negative 500x minus 400 for x between 0 and 0.2, and negative 500 for x between 0.2 and 0.4. And we can graph these functions. So there's t. And the tension again is just 0 the whole way. I just started doing that recently. Like if I try to scribble a dark line, it erases everything for some reason. And then the shear force. We had a value of negative 500. And then it jumped to a value of 0. And then the bending moment I don't have that plotted here. Can someone, okay, so we know, looking at this, that first subfunction is a linear function. And we know it starts out with a value of negative 400. When x is equal to 0, m is equal to negative 400. And so now to figure out where the other endpoint is, we can plug, where is it? We can plug 0.2 in for x, and we'll get negative 500. And so the function looks like that, and then like that. Any questions about those calculations?
The graph, or why just plug in linear graph?
Yeah, I'm just plotting those piecewise functions. And you can find online programs that'll do those graphs for you. You can do it on your calculator, you know. Any other questions?
I do have a question.
Yeah.
So basically, first step to do this problem, we always find external
Yes.
before doing internal.
Yes, that's right.
Right. Okay.
Yep.
So it's done external load.
External loads, and then go to the cuts. Yep. Yeah. Why are the what different? Between the one we just did and this one? This one has all these couples. The couples are what make everything weird. It has a couple at both ends, and that's what makes things weird. The other one just had two equal loads on the end and a load of double that in the middle.
Because like the graphs, they look like, in my mind, they look like kind of like if you took that board, put it right on the X of the graph, and you see kind of a graph of what's happening depending on the graph.
Mm-hmm.
So like you have some negative couples. And
Yes.
nothing, right? Or
Yeah.
constant.
Yeah, right.
If we were given all external loads, we don't need to do any rigid body calculation. We just find like if the Rx and R is given.
Yeah, then you don't, right, then, yeah. But most of the time you're going to have to do it like this. I think maybe every time you're going to have to do it like this. You're going to first have to calculate the external loads and then go to the internal load calculation. All right, so is there anything, so you look at this and you're like, well, interesting. How likely is it that I didn't make a mistake? Like you always want to have ways to sanity check your answers at the end. And so there are some ways that you can check these answers. So 8 checks. On your internal loads. The first one is at every point, dm dx has to be equal to v. So I'm going to list these all out, and then I'm going to go back and second, dv dx has to be equal to negative q. I haven't talked about what q is. We'll do that next. But Q is the downward facing distributed load function. For us, we didn't have any distributed loads in this problem, so the distributed load functions are 0 everywhere, which just says that dv dx has to be equal to 0 everywhere, and that's why our v's are constants. Third, at endpoints, t is equal to 0 if and only if there's no horizontal point force at that endpoint. Fourth, at any endpoint, v is equal to 0 if and only if, what do you think this one's going to say? Vertical, yep, exactly. There's no vertical point force at that endpoint. fifth at the endpoints. M is equal to 0 if and only if, what's this one going to say? No point couple. Yep, exactly. There's no point couple at that endpoint.
So how would that happen? Would that happen if you only had a horizontal force? Or,
That there'd be no point couple?
yeah.
Point couples mainly for us, I mean, we just did an example where there was an externally applied point couple of 500 Newton meters, but most of the time those are just going to come up at fixed joints, you know.
But what I mean is that 500 Newton point couple didn't do anything because we didn't include that because it was on the endpoint, correct?
Well, yeah, so if we, it did do something, even though we didn't use it in the internal load calculations because we used it in the external load calculations. So it shows up in the other calculations we did.
Oh, okay.
You know, by the time, even though this doesn't show up in our internal loads, the other external loads tell us all we need to know for the math to figure out what that is, basically, you know.
And wouldn't the 500 Newton force in the middle create a point couple as well? Because
Nope.
that is-
Not a, it creates moments depending on where your about point is, but it doesn't, you know, a moment produced by a force is different than a couple.
Okay.
A couple is this, you know, two equal and opposite forces. That 500 is just this.
Okay.
So it's a different thing.
We did change our internal load answer if we didn't have the 500.
Yes.
Oh, okay, so it would change.
That's right, because it would have changed our external load answers, and then it would have changed our internal load answers based on that. All right, so we still have a few more to go. And basically, the way we're going to use this, I mean, I'll sometimes ask you to do these checks on problems. They're good habits to get into, but it's a lot, you know. The more confident you want to be, the more careful you want to be with these, you know. The less you care about your answer, like you're doing work for someone you hate or something, then maybe just do a couple of them, you know. So 6. At an internal point, you know, not an end point. T jumps. Let me say that more quickly. T, sorry, everybody grabs their erasers. T is discontinuous. Only at horizontal point forces. What's 7 going to be? At an internal point. Yes. Yep. Yes, exactly. V is discontinuous. Only at vertical point forces. And then 8, what's that going to be? At internal points. M is discontinuous. Only at what? Point couples, yep. Such good quiz questions. Yes, you're right about that. And so it's 8. That feels like a lot to remember, but really what it is there's the two derivative ones, and then there's kind of two different things. One about endpoints that just goes down the list of internal loads, and one about the internal points that just goes down the list of internal loads. And this set of checks, I mean, I'm calling them checks, but they're facts that have to be true. If you look at 1 and 2, and then you look at the stuff about the endpoints and internal points and whatever, you probably, if it hasn't yet, it would pop into your head after doing these for a little bit, like, why am I going through all this effort of calculating at least the bending moments if I could just use Newton's second law to calculate the shear force and then just integrate that to get the shear force, right, and then just integrate that to get the bending moment. You know what I mean? So why not do that? Like, is there a problem with that? No, that's a perfectly valid way to do it. It's just that you end up, remember that every time you integrate, you have a constant of integration. And then you have to match that constant integration to the requirements from 3 through 8 about where there are discontinuities and where there aren't and stuff. It's a perfectly valid way to do it. It just isn't, it's not horribly worse than doing it the way we're doing it, but it doesn't really save you any time in the end, so we're going to do it this other way. But it's a perfectly reasonable approach. Oh, and so let's go through this last one we did and make sure that these checks follow. So first, at every point, dm dx has to be equal to v. So we'll go to cut 1 first. Dm dx is negative 500, and that's v. Check. Yeah. For cut 2, dm dx is 0. That's v. Check. So now we go, so 1 worked out. The second one, dv dx is equal to q. Well, we haven't talked about q yet, but there's no distributed load, so what this is saying for us is that dv dx has to be 0 everywhere, or in other words, v just has to be constant. For cut 1, v is constant. For cut 2, v is constant, so it holds. Yeah, you're right. I did not consider those. We're just leaving those out of all of this stuff. Yes. Yeah, we really don't have any way to analyze what's happening exactly at those point loads, but that isn't a practical concern because actual point loads don't exist. You know, even you sharpen a knife to the sharpest it can get, and you apply a force through that blade, it's still distributed over some distance. And so right at those points where we're applying point loads, mathematically weird things happen that don't happen in real life. And so where those point loads are applied, we don't care about, basically. Okay, so now we're done with the derivative ones. All right, so now at the endpoints, are there horizontal point forces at at either of the endpoints? Where is that? No horizontal point force at the left, none at the right, and so T should be 0 at both endpoints. It is at the left, and it is at the right. Okay, now vertical point forces. Are there vertical point forces at either endpoint? There's one at the left, but not at the right. So the shear force at the left should be non-zero, and it is. And at the right it should be 0, and it is. And now the bending moment. Are there point couples at either endpoint? At both. So we should have non-zero bending moments at both endpoints. We do at the left, and you can tell from the graph we do at the right. You'd have to, oh, no, you can see very easily. It's non-zero at the right, too. And now the internal points. So basically, we expect we expect the tension to jump anywhere we have a horizontal point force. We expect the shear force to jump anywhere there's a point shear force, but a vertical point force. And we expect the bending moment to jump anywhere there's a point couple. So inside, between the two endpoints, are there horizontal point forces anywhere? No. So we expect T to be continuous over the whole thing. And it is. It's just 0. Are there any vertical point forces anywhere? Yep. Right at the middle, there's a vertical point force. So we expect a jump in the shear force at the middle. And it's there. And then the bending moment. Are there any point couples anywhere between the two endpoints? Nope. And so we expect the bending moment to be continuous. And if you look at the graph, it's not differentiable, but it's continuous. Any questions about the checks? Yeah. Okay, so there is, a couple. It's not acting at a single point. Right. So when you see a point couple will look like this. And there's nothing like that, so. Any other questions? All right, so now distributed loads, internal loads with distributed loads. The first key idea is we're going to represent these distributed loads in terms of these distributed load functions Q. So we're going to find the function Q of x that represents the downward distributed load. So for example, if you have a rectangular distributed load, let's say that the length here is 2 meters and this distributed load is 5,000 newtons per meter. Q is the function of the line that defines like the upper border. So Q is the function of the shape's top. So in this case, as you go from, okay, so we'll call this point x equals 0. And positive x goes this way. So what's a function that represents the height of this line at every x value? It's sort of a trivial question. Just 5,000, it's constant. So in this case, q of x is equal to 5,000. Okay, so now how about this one? If you think you're so smart. So let's say this is 4,000 newtons per meter. Let's say this is 2 meters. Well, q of x is going to be, a linear function. So I'm just going to write it like this. Q of x is equal to mx plus b. This is x equals 0. Positive x goes to the right. The slope is the rise over the run. So we're rising 4,000 over a run of 2. So that's 4,000 over 2 times x. And then what's the y-intercept of that function? When x is equal to 0, what's the height? 0, yep. So q of x is equal to 2,000x. Any questions about that one? Yep. If it was upwards?
If your triangle is just split.
Yeah, okay. Yeah, we'll do one like that. So then you're going to have a y-intercept. You're going to have a negative slope. So let's say this is 10,000 newtons per meter. Let's say this is 4 meters. So again, this is a linear function, so we have mx plus b. The slope is rise over run. The rise is negative 10,000. The run is 4. And what's the y-intercept? 10,000, yep. Any questions about that one? And then one more. We haven't had to think about weight this way yet, but now we're going to have to. So let's say we have a beam with a mass of 150 kilograms. Up until this point, we've always just treated weights as point forces, but they're not really point forces. They're really, an infinitesimal force acting at every increment of mass. So really, they're distributed loads. And if you have a beam that's the same thickness everywhere. It's just a uniform distributed load. It's going to have the same value everywhere. Okay, let's say the length is 5 meters. Then you can rewrite that as a distributed load of, well, the total weight is 150 times 9.81. So mg is 1471.5. And so the distributed load is 1471.5 divided by the length. So 1471.5 divided by 5, and that's equal to 294.3 newtons per meter. And now that we have that, what's Q? Not even X, just 294.3 because it's constant.
Do we still look at the center of mass, the location of X, center of mass?
That is still going to come up in these calculations, yeah. And I'm not done talking about what's changed to make us have to treat weight like a distributed load, and when we can treat it as a point force and stuff. But that is sort of it's an odd new wrinkle, you know. Okay, and here's the last one. What number was that? 4. So number 5. You have a distributed load of 1,000 newtons per meter. You have a length of 1 meter. And you have a mass of 50 kilograms. So we'll rewrite that. So we have the distributed load, triangular distributed load. I'll just put that on top. The weight is 50 kilograms divided by 1 meter times 9.81. So we have another distributed load. Like that. Now Q for the triangular distributed load is 1,000x. Q for the rectangular distributed load is 490.5. So Q of x is 1,000x plus 490.5. Yep.
What would we call Q again, the name of it?
Uh,
You said something, I think it was in the.
distributed load function, or
Distributed.
function of the downward distributed load. So yeah, the default is always down, just because that's what we're going to always. I don't think there are any problems where it's facing any other direction. Okay. in general. So this is the question you were just asking. When can you make the jump to treating a distributed load as a point force? Okay, so now all of a sudden we're saying weight is a distributed load, but we've always treated it as a point force. Now it's all of a sudden we're going to have to treat it as a distributed load again. When can you make that jump to treating it as a point force? And you can do it once you've chosen the body to isolate. For Newton's laws. So let me just go through an example with a distributed load, and I'll try to point out what would go wrong if you didn't follow this rule. All right, so let's say we have a cantilever beam. It's 2 meters long, and it has a mass of 100 kilograms. What are the internal loads? One thing that, Ryan, you sort of noticed before is where are the external loads we have to calculate? Only at the wall over here, right? And in this case, that wall is on the right end. And we never use the stuff at the extreme right end of the beam in our internal loads calculations. So if you ever have a problem where all of the external loads are on the right side, sort of a time saver, you know, you can skip the external loads calculations and just go right to the cuts. You understand how that works? No? You don't, if you...
Why we do that? Why we skip external loads?
Well, just in this case, if you look back at the internal loads calculations, whatever is happening at the right end, it never appears. And so it just won't matter in our internal loads calculation. So we can do internal loads calculations without figuring out what's happening on the right end. And so if the only stuff happening is at the right end, then you don't have to calculate external loads.
If it was this way, then we need to know what's
Right.
happening
Right.
on the left end.
So I'm going to skip the external loads. Because they're on the right end. Okay, so let's think about where these subfunctions could change. The endpoints. Are there any other places where there are point loads or where distributed load functions change? No, there's a distributed load, but it's the same everywhere. It's just that weight. And so n is equal to 2, which means we just need one cut.
But why is it n equal 2? Like, this one we had n equal 3, this one because we don't have force on the left side?
Yeah, we don't. It's because there's nothing happening in between the two endpoints. Okay, so cut 1 is valid for all x's between 0 and 2. The distributed load is 100 times 9.81 divided by 2. So 490.5 newtons per meter. And then we have tension, shear force, and bending moment. And now that we've chosen the body to isolate, we have our free body diagram. We can treat that as a point force. And so I'll redraw this. We have these. The length of this piece is x. And so that rectangular distributed load has a height of 490.5, a length of x, and so the area is 490.5x. The centroid is right in the middle. And so we have a downward force of 490.5x acting right at the midpoint. Yep.
Isn't that greater than 490.5? Because in the problem before, we have the triangular distributed load and the rectangular, which being was 1 meter long, we also have 490.5.
It was a, I think then it was just a smaller distributed load, wasn't it?
It was still the mass, wasn't it?
That was just a mass, and this one you only have a mass. That one you
Okay.
have distributed by mass.
But would that affect the cost because now we're having force on the middle, so would that affect the cost?
The cut? Yeah, it's going to affect our calculations. This is going to be an important thing. And so this distance is x over 2. This whole distance is x. And so now if we go to Newton's second law,
Would that really be x over 2? Wouldn't that be just halfway? Wouldn't that always be at 1 because it always acts at the midpoint of v?
no, it always acts at the midpoint of our piece.
Okay.
Bless you. So the Newton's second law says 0, negative 490.5x plus t0 plus 0, negative v is equal to zeros. So t is equal to 0, v is equal to negative 490.5 x. And then the moment equation, uh, 490.5x has a moment arm of x over 2. Would that produce a clockwise or counterclockwise rotation? Clockwise, so that's negative, so that's negative 245.25 x squared plus m minus vx equals 0. And so m is equal to vx minus 245 x squared. This is plus. I didn't move it over. And so if you add those up, you get minus 245.25 x squared. Okay. Time's up. Any questions? Say no, because time's up.